Okay, I'm going to go through enthalpy of formation, and then we're going to also look later at enthalpy of combustion. But what do these terms mean, and how would you write the equation for enthalpy of formation? That's the topic of this video. When we're doing enthalpy of formation, we're talking about forming compounds, but forming them in a special way, forming them from the elements that make that compound, and forming them from those elements in their standard states at 25 degrees C, that's room temperature, 1.0 atmosphere. So under normal conditions, what are those elements like? And let's look at that first. Hydrogen is 1 proton, 1 electron. That's not the stable state of hydrogen. A hydrogen atom by itself, that's not stable. If we look at the Lewis, what does that hydrogen need? It needs a full shell. For hydrogen, that's 2 electrons. So it finds another hydrogen, bonds together, that is stable. The H2 molecule is stable. And at room temperature, 1 atmospheric pressure, what phase is hydrogen in? It's a gas. So we say the standard state of pure hydrogen, the element hydrogen, is a diatomic, because 2 hydrogens, gas. The same goes for N2. It's a gas, right? It's diatomic. 2 nitrogens bonded together is the stable state. Nitrogen by itself, not stable. So that would be its standard state. Nitrogen gas is everywhere, right? It's the main component of our atmosphere. O2 as well, diatomic gas. F2 is fluorine. So these are the 7 that exist as paired up, because they have to have that full shell to be stable. And then chlorine gas, also diatomic. And then bromine is actually a liquid, coming up as to why that is. So these are the standard states for these elements. And then iodine is actually a solid. Oops, bromine 2, iodine 2. But they're all paired up. That's if you have that pure element in their standard states at room temperature, 1 atmospheric pressure. Those are the states. There's 7 of them, 1, 2. Right? That are paired up. Other things, for example, carbon. What about carbon? In its standard state at room temperature, what is the standard? Carbon can make up diamonds, but mostly it's like graphite. It's just solid carbon, just a collection of solid carbon in the solid state. That's its standard state, as well as a lot of them. Even something like sodium, which normally in nature it's Na+, right? It has a low ionization energy, gets rid of that electron. But if I say it's the element, not the ion, it would be solid sodium. So enthalpy of formation is taking these elements in their standard state and building compounds. And then what kind of enthalpy change is there? So let's look at a very stable. Enthalpy of formation tells us something. It kind of helps us with how stable is that compound that I just made. One of the most stable is CO2. If I want to say what is delta H, the enthalpy of formation of carbon dioxide, I look it up in a table. And there's these tables, and I have looked it up. It's negative 393.5 kilojoules per mole. Sometimes it'll say kilojoules per mole. I'll write it. That is the enthalpy of formation of carbon dioxide. That means doing this, taking solid carbon, oxygen in its standard state, that's O2, which is a gas. Oxygen is a gas at room temperature. And making CO2, which is a gas, I will see an enthalpy change of negative 353, very exothermic. So if I lower the potential energy, that would say carbon dioxide is really a more stable state than the elements in their separate states. So some of these things are, this delta HF can tell us how stable is that compound. Let's do 2 more. What about H2O, liquid state? How stable is water? It seems like it's pretty stable because water is everywhere. So I look it up in the tables. Negative 285.8 kilojoules per mole. How would I write that? That's per mole. So I'm going to make 1 mole of H2O, liquid. I'm going to make it from its elements in their standard state, and only 1 mole. So the coefficient has to be 1. All right, so I H2 gas, and the other element has O2. I'm going to take hydrogen in standard state, oxygen, pure oxygen element in standard state, and I'm going to make water. The enthalpy change is going to be this. But wait a minute, it's not balanced. So normally, if we were to balance this equation, we say, okay, make this a 2, this a 1, and that a 2, because all the coefficients have to be integers, whole numbers. But for this, since the key is I'm making 1 mole of water, I can use fractions, right? Because this needs to be 1. Since this needs to be 1, I can have these be fractions, so you're making 1 mole. So these are two we know carbon dioxide and water, very stable compounds. So I can start to see from enthalpy of formation, if something is unstable, higher potential energy generally is less stable. So these have a drop in potential energy when they're formed from their elements. So something like acetylene, which burns very hot, it's used as a welding torches. Acetylene is C2H2. And so this is a really reactive gas, and I looked up its enthalpy of formation. Positive. That means from its elements, you raise the potential energy, which generally means this is less stable than the elements in the standard states. It's got a positive delta HF. So this kind of enthalpy of formation can help us with how stable is that compound. Not so much. So let's form it. So I'm going to form it from carbon in its standard state, it's just that, and hydrogen gas. That's the standard. So there's the 2 elements that make acetylene. C2H2 gas. Acetylene is a gas. Let's balance it. 2, 1, 1. And so enthalpy of formation is that. It's just, okay, if I were to form it, what would from elements in the standard state, what is the enthalpy change? So if we see something not a very stable compound, we can see it actually raises in enthalpy. Generally, the higher enthalpy is less stable, right? So if I see delta HF is a big negative number, then that's a big hint. All right, the other one that we're going to look at here, enthalpy of combustion. So this is what is the energy change, and these are all exothermic, right? What is the energy change when burning 1 mole of the compound? Right, so that's called, just like enthalpy of formation was saying, okay, what is the enthalpy change when forming 1 mole of a compound from elements in the standard state? Enthalpy of combustion is, okay, how much energy do I get? They're all exothermic. When I burn 1 mole of a compound, there's tables with these, right? This is used frequently in industry, saying, okay, I need a fuel for this thing. Let's look at enthalpies of combustion, and we can start to calculate how much energy with each fuel. There's multiple things to look at when choosing a fuel. One is cost, right? But this is kind of a way of saying, okay, when this thing burns, how much energy is released? So let's look at a couple of them. In fact, let's start with acetylene. So here's the equation for enthalpy of formation. What about enthalpy of combustion? That means I'm going to take C2H2 gas and burn it in air. That's O2. Everything, so a common thing, and it's part of the AP curriculum to know, if I burn a hydrocarbon, which means something with carbon and hydrogen, the products are always CO2, gas, and I'm going to go with liquid water because standard states. All right, 2 carbons, let's make 2 carbons. 2 hydrogens, I'm good. But wait a minute. 2 times, that's 4 plus 1, that's 5 oxygens. That's not going to work. because I can only add oxygens in pairs. So let's double them. 2, make this 4, and this 2. Right, and then what do I got? So now I got 8 and 2, that's 10, so 5 oxygens. And so that would be the equation for, balance equation for the combustion of ethylene, of acetylene. But when you're writing the formula for delta H, the enthalpy change of combustion, it's for burning 1 mole, not 2 moles. So I got to cut everything in half. Take that 2, make it 1. Instead of 5, it's 5 halves. So these are the kinds of things where you can see, and it's the only time when we will use fractions as coefficients in a balanced chemical equation. Only when these kinds of diagrams. 4 halves is 2. 2 halves is 1. And so that would be my enthalpy change for acetylene, and I did look up the value in these tables that you find everywhere. Negative 1301 kilojoules. Pretty big, right? So this burns hot, right? There's a lot of energy coming out with that. What about something like enthalpy of combustion of methane? Let me leave that one up, and I'll write it up here. You can write it below. Methane gas is used all the time. It's easier to get than acetylene is just kind of more expensive. O2, CO2 gas, and water, liquid, going with standard states at room temperature. So I'm burning it, and then for both these, burning it and then bringing the contents down to room temperature. Balance it, 1, 2, 1, 2. So it's already a 1, so I don't have to do anything with it. It's 1 mole. When I burn 1 mole of methane, how much do I get? I look it up in the table, and it says enthalpy of combustion for methane is negative 890.8 kilojoules per mole. And so these are the kinds of things. So if you say, oh, enthalpy of combustion, put the substance here, it's reacting with oxygen. If it's a hydrocarbon or something with C, H, and O, the products are this, and you just balance it, but make sure the coefficient of whatever it is, the compound that you're combusting, has the value 1 if you're trying to write the expression for enthalpy of combustion. And we'll practice that some more.